pleasure to introduce the keynote speaker of this session, Professor Gabriel Spalding from Illinois Wesleyan University. Gabe got his PhD in 1990 from Stanford of the East, otherwise known as Harvard. His thesis topic was fabrication and characterization of high-temperature superconductors with emphasis on quantum mechanical tunneling measurements. Gabe has a bachelor's in physics and mathematics from Washington University. Since 1996, he has been a professor at Illinois Wesleyan University, Department of Physics. He is a fellow of the American Physical Society, fellow of SPIE, and American Association of Physics Teachers. Without further ado, let's hear what Gabe has to tell us this morning.
Well, hello. Do you recognize my picture? Now, the annoying thing is that with this camera, I mean, most cameras give you a picture of how you looked in the past, right? Most photographs show you the way you used to look. If I use this camera to take a picture of Andy or Tuan, then they look pretty much the way that they do now. I look different. Just another day at the office, faster than light imaging and violations of local realism. Oh, with a title like that, we should, for assessment purposes, begin with a pre and post test, which consists of one question only. Are you really annoyed with me yet? How many people are really annoyed with me yet? Okay, we'll see how this goes. Yeah, I teach at Illinois Wesleyan University, and with my students and our collaborators, we do all sorts of strange things. It's one of those talks. Now, the problem begins with how we train physicists, you see. This is where the whole thing begins. You know, these physicists are weird. This is the most popular text on quantum mechanics. And on page 3, David Griffiths asks us to consider a particle, maybe it's an electron, maybe it's a photon, that's described by a wave function shown up there at the top right. And when you look at this, you say, okay, there's a significant probability that if you measure the particle's position, you'll find it at position A. But suppose that out of many measurements on identically prepared systems, you make a measurement, and you happen to this time find the particle at position C. All right, that's fine. The question is, where was the particle just before you made the measurement? And Griffith suggests that there are 3 possible answers to this question. The realist says that, well, just before you made the measurement, the particle must have been right around position C. It must have been right there. On the other hand, the orthodox physicist says that the particle wasn't really anywhere. It didn't have a position. And at this point, some students are annoyed. And then if you flip the page, there's the third position, which might make you happy. It's called the agnostic position. And it says, asking a question of this sort makes no sense. Because the only way to answer it is to do the measurement, at which point you're no longer talking about what happened before the measurement. And that would tend to make a lot of people happy, except that the theoretical work of John Bell said, you know what, shocking as it may seem, there's a class of real experiments that could be done from which it would make an observable difference whether or not you had this case or that case. And it rules out, therefore, the agnostic position. You're not allowed to have that as a choice. And it's only within the last year or two that the last loopholes have been removed by real experiments saying, now, this slide is my suggestion for a T-shirt that I want some entrepreneurial soul to help me make. When we tell students that real experiments following up on Bell's theory have led us to conclude that measurement can perhaps collapse an extended, perhaps entangled wave function at something maybe faster than the speed of light. If any of those words make sense or not, I mean, you can argue. How do these students react? Well, they come in 2 classes, and using the notation of the discipline, you see, the students are actually in a superposition of these states. They're actually entangled until their measurement is performed. You see, there's a very important role for hands-on instructional labs in teaching quantum mechanics. So, trademark Gabe Spalding. There you go. My wife and I, and now Andy Dawes, we've shipped out 420 of these single photon avalanche diodes, SPADs, so that people, you, can do the experiments yourselves, all the way through violations of local realism. We think that's very important. And if your institution does not yet have some of these, send me an email. The organization Alpha, the Advanced Lab Physics Association, is really just a community of us, folks who deliver or care about the advanced instructional labs beyond the first year of university. So it's advlab.org, advancedlab.org, beyond first year of university. And we are a physics organization. I was the first president of Alpha, and I'm still the PI on our NSF grants, though distributing these is something that was outside of our NSF support. At Lawrence University, they every summer have a camp for prospective students where they use these for hands-on experiments in quantum mechanics. So these are high school students, right? In Germany, it's routinely a part of the curriculum with high school students to do these experiments. This is not the way I was taught physics. The world has changed. There is a whole new generation of textbooks, including ones for non-majors that use cartoons rather than equations to walk you all the way through Hardy's test of local realism. And whereas that text by David Griffiths mentioned on page 3 an experiment, that was the only mention in the text. The new generation co-values theory and experiment, I think, to the benefit of all. And what we see are departments reverse engineering the curriculum, saying we want students to do some very sophisticated work. How are we going to reconsider what we do to put them in position to do that? John Townsend of Harvey Mudd had an upper-level quantum text, but then this one is for the sophomore level. And we've used this at our institution. In Chapter 1, they're doing these single-photon quantum mechanics experiments. Chapter 1, third semester physics. Some people doing it with high school students. Regardless of what level you're introducing these things at, we think you ought to be doing a lot and building up to higher level sophistication. So we need to change the way we teach. So I'm a big fan of SPADs. You know, every mad scientist has a plan for world domination. This is mine. I'm Johnny Appleseed for SPADs. These single pixel SPADs are the ones where we've shipped out 420 so far, and we're ready to ship out more any day. In fact, we have a huge waiting list. Over on the right, I spent my sabbatical year this past year working with Quantic, a large collaboration, many professors, led by Miles Paget at the University of Glasgow in Scotland, where they have developed arrays of SPADs, camera. I'm going to talk about weird cameras. I like SPADs. I'm distributing these. One of these is now coming to my lab, maybe coming to your lab soon. Now, this is not using a weird camera. This is using my iPhone camera. I went down into the undergrad lab, and I got out a narrow slit, and I shine a laser through it. You see this band of light, and then I close that slit, and I open another slit, and I see a band of light, and I open the two slits, and what you see is that some of the places which were formerly bright are now dark, and the energy that would have gone there has sloshed over, and so some of the other regions have become brighter. It's not hard to explain something like that when you have a wave picture of light. You say, okay, yes, from the two slits, you had different distances the waves had to travel, so depending upon where they arrive, they get out of phase, or maybe they're in phase, so you get destructive or constructive interference. But how do you explain this within a photon picture of light? Well, the problem is the word photon typically brings to mind a picture of a particle-like ball, or perhaps a well-defined ray that describes a ball's trajectory. And such a photon cannot exist, as the uncertainty principle requires us to modify these mental models. Yet the notions are so widespread that they've led to suggestions by Wallace Lamb, professor here, that physicists ought to receive special training and a license before being allowed to use the word photon. So we have to look back at how we train physicists. Now, some instructors will say that given a choice, a quantum particle will take all possible choices weighted by their probability of happening. They may go on to say that the only physical description possible of the propagation of each photon is that of an extended probability wave. Now, a probability wave itself is not an entirely familiar concept when we're starting out. I mean, if you were thinking of a crime wave sweeping a city, that would be a similar idea. Or maybe an epidemiologist would talk about a probability wave to describe how an epidemic would propagate. And in each case, the probability wave is not a localized entity, and yet each individual crime or each individual case of contagion occurs locally. The probability wave describes correlations, not correlata, to quote David Merman. In the same way, we describe how a quantum particle propagates, not in terms of a real entity, but instead a probability wave. Yet when you measure the deposit of a particle's energy, it will always be localized. So here is our recent experiment published in the American Journal of Physics. We have only one detectable photon in the path to the camera at any time. And on average, there are far fewer than one photon in the path to the camera at any time. And the statistics describing the transmission along the line to the camera does not show any tendency for bunching in arrival times, quite the opposite. So the fact that we end up over time building up this interference pattern, which cannot mathematically be described as it went through here or there, is sort of interesting. I should note that no commercially available camera has the dynamic range required to directly produce video recordings of true single-photon two-slit interference, because readout noise significantly contaminates or overwhelms the signal. Here the noise levels are significantly reduced by turning on the camera only when the presence of a photon has been heralded by the arrival of a separate entangled photon at one of my single pixel SPAD detectors. That is, this particular experiment, we need to talk about the setup. It may involve something a little new for you. We have a photon source, and it sends out, let's say, a photon. Let's call it Hermione. And Hermione is very logical and comes along. But then you see that there's a crystal where the photons that change color. This mother photon gives rise to two daughter photons. Let's call them Harry and Ron. And we have a beam splitter. These photons, Harry and Ron, it's unfair to really give them these two separate names because I can't describe Harry and Ron separately. They're only constrained by the conservation laws. In combination, that turns out to be the key to why they are entangled. But what we will detect is the case where a photon goes over to my single pixel SPAD here, and that's going to be used to turn on my camera over here. There's a delay line to account for the insertion loss, the electronic delay times, and so on. So these will be in coincidence. So you have Harold going this way and Ronald going that way. You might notice, however, that the camera that took that picture is not the path that contains the two slits. The photons that went to the camera never interacted with the diffracting object. Never interacted at all. So this is called ghost diffraction. And the word ghost references Einstein's concern over spooky action at a distance. Are you annoyed with me yet? Okay. Let's see. What's going on? It works so well because we're only going to turn on the camera when the arrival of a photon is heralded by the arrival of something over there. Now, Harold and Ron were created at the same time from Hermione, right? So they are correlated in time. They were created at the same position. And the conservation laws say that their transverse momenta must be anti-correlated. If we did not use this triggering of the camera, turn that off and just leave the camera on all the time, what we would see there would just be a big circle, would be the shape of the beam. We're throwing away some of that information when we're saying, no, only turn it on when you had this photon over here that made it through the two slits. And the correlations between their transverse momenta are why you saw the diffraction pattern over here. Correlations were the key. Now, maybe you're not annoyed with me yet, but you're about to be. In a diffraction pattern, which you do this experiment with two slits in first year physics, you project onto a wall and then you measure the distance from the slits to the wall and you look at the spacing of those fringes. You remember that experiment? So we could calculate the spacing of those fringes if we know the wavelength n, we know our slits, and we know the distance to the wall. What distance to the wall should we use? This is where you get annoyed, because Klitschko and Xi's work on ghost diffraction said, what you need to do is to use the distance where when you measured this photon, when you collapsed that wave function, you had the other one go backwards in time through the slits back to the crystal where they were entangled, which acts as a mirror, and all the way over to here. And that works. And you say, I don't like this. No, what? Okay, so this Klitschko advanced wave picture does describe the experimental results of our work in ghost optics, but we're only claiming that ghost diffraction illustrates how the uncertainty principle applies to the biphoton wave function, or probability wave, a constraint placed upon transverse position within the heralding arm reveals transverse momentum information in the ghost arm, in the camera arm. Of course, we can use lenses to modify the setup so that our camera is virtually positioned at the plane of the two slits. When we do that, we see that while there is some noise still in the system, so occasional spots elsewhere, really what the setup is statistically showing is that photons went through one slit or the other when we look. Right? When we have this setup such that we're allowing them to deposit their energy in a plane that is essentially the plane of the slits. Then, excepting for the remnant noise signals, we see that each time the photon goes through one slit or the other. On the other hand, when our camera acts instead as a distant screen, it seems as though we can only describe the result by saying that the correlations or probability wave describing the single photon went through both slits and interfered with itself. Again, in our version of this classic experiment, we are triggering the camera only when my single pixel SPAD detects a second photon. The single pixel photon has no information about an image. Neither one of these detectors on their own can give you the image. It's the correlations that are the key. The fact that we have this high degree of correlation that came from the conservation laws. Now, there are actually a whole series of movies which you can access and download from my site. It also references our American Journal of Physics article. That's, so many people, most highly read article for the past 4 months in American Journal of Physics. A lot of people seem to be enjoying it. You would probably enjoy it. I think you go read the article. But you're bothered by this stuff quite a bit. Let's use the same equipment in a completely different experimental context to demonstrate at least one sort of backwards time travel, because that's what bothered you. Even saying that, you may be more and more annoyed with me. In this experiment, we vary the angle of incidence of a pancake of light upon a diffusely scattering screen. So this is our pulsed laser. This pancake of light is about half the width of one of your hairs. Well, it's a very thin sheet of light moving along, and when it has moved up to here, then the camera will see a spot over on the left side of the screen, right? And when it moves up further, that spot will move over towards the right side of the screen, right? Now, it's all over pretty quickly because this is moving at the speed of light. So if you want to do this kind of experiment, you're going to have a camera with wicked speed. I should say we did the experiment twice with 2 different kinds of cameras. One using the intensified CCD camera, which we could turn on and off very quickly, and we put a delay generator on the gate. So the gate time was 200 picoseconds, but we could step the delay on that gate of turning on the camera in 10 picosecond steps and back out higher time resolution. We also used the homemade SPAD array camera that I said maybe is going to be in your lab soon. And every pixel on that is a clock with time resolution better than 55 picoseconds. Okay. Turns out that a spot of the sort that you imagined seeing moving along that screen is not a real thing. It moves faster than the speed of light. What is it? It is an intersection between a real thing and this screen, the diffusely scattering screen. Suppose that our pancake of light has reached this dotted line. That means our point of intersection is over here on the left. And over some time interval delta t, that wavefront is going to move up to this point. And that means that the spot must have moved along the hypotenuse. It has to have moved faster than the speed of light by the triangle inequality. Every spot moves faster than the speed of light. It doesn't violate Einstein, doesn't violate special relativity. You can't send information from this point to that point in this way. There's no problem with it. And it's simple stuff. We can back out, just trig, what is that speed? It has to do with what is the angle of incidence. It only approaches the speed of light when you go to glancing incidence. But it should make you think of this man. George Sudarshan, in 1962, hypothesized a faster-than-light particle, which we call the tachyon. Now, the thing about the tachyon is it's not a real thing. But he said, if it were, here's how it would behave. Here's how it would look to you. It would appear to be moving backward in time. So, could we possibly observe experimentally? Can we make a movie of something going backward in time in a real physical sense? Well, it turns out that what matters is not the speed of the spot, but the component of the speed coming towards you. So if you're over here, you're the detector, we have to break that spot motion into components coming towards you, and the spot is also moving partly transverse to that direction. Again, it's just simple trigonometry, and we can back out what is the component of the speed coming towards you. Why is that component what matters? Well, here's our blue diffuse scattering screen, and at one point in time early, our spot is off on the left, right? We agreed upon that. When our wavefront has hit this point on the screen, it causes a reflection. There are emanating wavefronts that are moving out in all directions. It's a diffuse scatter, but including towards the camera at the speed of light. But the spot has outraced those wavefronts. So what's emanating from this point will outrace those. And therefore, you must see these spots in time-reversed order. Do you agree? So, all right, it's just simple trig. What matters is this component of the speed, not just the spot speed, but we found both of those things. We can combine them, and what we should see would be time reversals whenever the angle of detection is greater than the angle of incidence. So we did the experiment. The blue lines are the trig that I just showed you. The red data points actually are uncertainties largely in the angle measurement. But, you know, it was kind of a way to calibrate our cameras, in a way. There's something else. The effects that we're seeing are really very general. It doesn't matter what ultra-fast imaging technique you use. There are lots of ways to have faster-than-light imaging, which is what we have. And they have a lot of possible applications in biomedical research and allowing for imaging transient events from the scale of cellular organelles and smaller, all the way up to work with telescopes looking at astrophysical phenomena. Yet, all such methods are going to have to include an awareness of the effects that we're discussing. Whether you're applying ultrafast imaging to fluorescence lifetime imaging microscopy or anything else, we know that regardless of the emitter's speed, it is not possible to unambiguously determine the kinematics of an event from imaging and time-resolved measurements alone. So, all right, that's all in red, a warning. By the way, if we look at a screen that is curved inward, we expect to see two spots. Why is that? Well, remember, when we have your detector over there, if I bend it this way, now the spot motion is largely transverse to you. The component towards you is reduced, so you ought to not see that go backward in time. You ought to, in fact, see this spot move in the correct direction. Whereas over here, where I bent it that way, you ought to see it go the wrong way. So you ought to see these two spots come together, and we ought to see spot pair annihilation at an event horizon. So here is the world's first observation of exactly that, and you have now seen a movie of something going backward in time. The stuff moving from your left to your right was going forward in time. The stuff moving from your right to your left, you know, was not, if you were sitting on that screen, let's say it's a water tower 6 kilometers away, you know the wavefront moves from your left to your right. But when you're that distant detector, it has to do with how the information had to move to you. Your time is not my time. Your sense of what is future and past is not the same as mine. Even so, I should point out that this is not Einstein's special relativity going on. This is a simpler time-of-flight effect. Einstein gives us deeper truths. By comparison, what I've shown you is trivial. But I still think it's actually a good way to begin teaching relativity, because it depends upon no postulates. That's what trips students up when we start teaching these things. This is postulate-free, so I'll be using these videos to teach special relativity from now on. And if you bend the curve, the surface in the other way, what you get are spot pair creation. So here is the world's first observation of spot pair creation. Now, in addition to having a little bit of fun with these things, I should point towards my research student. Now, Joe was an undergrad. He was not involved in the design of the spat array cameras, but he did get exposure to that, which led him to choosing what he wanted to do for his PhD work in ECE at University of Illinois, where he's begun this past semester, and he's got Gabriel Popescu as his advisor. He was not responsible for the slight misalignment of our laser that meant there was more light on one side than the other of our screen. That's why those two spots didn't have equal intensity. He did measure all the distances and angles. He unpacked the pixel by time step data cube. He learned MATLAB. He did the computer-based tracking analysis and propagation of uncertainties and helped write the paper. To me, the experience was very important in sending him to the next level with enhanced engagement. It's why he's doing what he's doing. But it would not really substitute for a foundational curriculum of laboratory instruction. And what I'm really getting at is I want you to think about your own students. I want you to ask yourself whether their research experience should be considered as a substitute for the sort of broad grounding a full curriculum of hands-on lab instruction can provide. Unfortunately, this is where you see a huge difference between programs. Let's look, and I've looked at all 752 degree-granting institutions that give physics degrees in the United States. I can say that there are quite a few, like this one, which is Amherst College, where beyond the first year of university, they offer one hands-on instructional lab course. Yale, same way, one. That's not enough. What they are doing is they are relying upon research experiences to substitute for a curriculum, and they play different roles in student development. At your physics department's next meeting, propose that you cut all coursework in quantum mechanics and instead expect students to pick it up from research experiences. No. So at Illinois Wesleyan University, we try to construct a spiral curriculum where students are getting lots of different experiences that couple to many different things. The way we did this is we told people in the department, don't try to do too much. Maybe just add a lab here or there. And as soon as we lowered the bar, wow, they instantly did all kinds of things. They weren't expected to do all kinds of things. And feeling like having to develop a whole lab course, it put them off. But as soon as we said, just do one or two things, instantly they did the whole thing. So this class I'm very concerned about. I'm teaching that starting Wednesday. It's a hands-on lab course. Now this is just showing the first 462 of the 752 institutions I looked at. I can tell you that in the whole distribution, more than 100 physics degree granting institutions have 0 hands-on instructional labs beyond the first year. The number that have 1 is greater than 0. The number that have 2 is greater than 1, but then it crashes. And what about optics? These places do have pretty much all a junior level optics class, but the percent that have a hands-on lab component is negligible. Nationally, we are not able to have the impact upon the world that we should have if we do not change the way we teach. So, we need to change the way we teach. Let me be really annoying you now. As a provocateur, I might argue that the role of some bachelor's engineering programs is to produce people who function as interchangeable cogs in the larger service of industry. Undergraduate physics students are needed by society to play a different role, even if, like my student Joe, they may go on in engineering. What they bring to the table should be a generalist background. The world needs this. They need you to be trained in this way. Now, I'm not saying physicists are better than engineers or that we need more of them than engineers. We don't. And they aren't. But they play a different role. We need to appreciate the role that they play, which requires a rather broad education. So I am the rising vice chair of the National Committee on Physics Undergraduate Education. And after a year of that, I'll be the chair. And so I'll be in a position to help do certain things. And one of the things that is my first task is to make sure that every new faculty workshop, every departmental chair workshop has this document, which is a tool, a framework consisting of 6 goals that when you think about them and unpack them and think about all that is really needed for your curriculum of hands-on laboratory instruction, you cannot possibly do in one semester. This is a tool for us as faculty members designing our lessons plans for instructional labs, and also a tool for departmental self-study and reflection and external review. It can be really helpful to be explicit about which goals your program aims to address and where in the curriculum these various goals should be or will be addressed. So for your consideration, there's a website. Download it. We want a spiral curriculum, one that revisits, reinforces, and refines student understanding of many things. You need exposure to a vast toolkit in order to have a solid foundation for a career as an experimentalist or as a theorist. You need to understand these things. There are models out there. There are lots of them. But in order to develop these sorts of things nationally, it's going to take a lot of support and a lot of conversation. It's going to take a village. It's going to take us working together. So the question is, what can you do? And the first thing you should do is go to advlab.org. You are a member of the community. Join the community. Share your expertise and share your questions. Say, I would love to do this, but I'm a little put off by the time it would take, and here's what we'll do. We'll say, okay, we've got somebody who's already doing it in the nation somewhere. Whatever you want to do, somebody's doing it. We'll put you together. For 2.5 days, you'll have a complete parts list. Alpha will organize all the logistics. We'll make sure that after 2.5 days, you're ready to go back to your own institution and implement this in your curriculum. It's good use of your time, very efficient, and we'll help pay for the equipment to go into your lab. So we started doing this in 2010. Our first immersion program, which is what we call these, was at Dickinson College. And interestingly, the immersion mentor teaching other faculty members how to do these single photon quantum labs was a theorist. David Jackson, the editor of American Journal of Physics, said this is important for him as a theorist to do and to have as a part of the curriculum. Now, this past year, we had University of Arizona. Last year's implementation of this program had hands-on laboratory component for these instructors doing these labs. We didn't just do it during the winter at 2 sites. We did it during the summer at lots of sites, doing lots of different modules. You say what you want in your curriculum. We set it up. There are lots of things. Just during this one past summer alone, next summer, it's a much larger and different list. Every year we're doing this. And we pay the mentors. We organize all the logistics. We lower the bar for this to happen. We make it happen. We'll pay $1,200 per mentor. And so far, more than 1/3 of all the programs in the United States have taken advantage. We're changing the world. For every one of these modules that we have an immersion on, we have a lab wiki where you can go. You can be part of a public conversation about how to implement this yourself. Your own questions are part of a larger conversation. Every topic. And it's a growing list. Within 18 months of taking one of these immersions, our post-surveys say, hey, more than 60% of these people have implemented things. And when you think about the time it takes to put something new together, that's awesome. We are not limiting ourselves to cheap experiments. We do always have some very cheap experiments. You can demonstrate the wave nature of the electron using a $50 experiment with gold wire. You can go all the way up to these single photon quantum experiments, which are more than $25,000 to implement the full thing all the way through Hardy's test of local realism, though you can do cheaper things and implement them in bits. We think it would be a disservice to the community to only be doing the low end. And it turns out that we sell out the immersions on the high end every time they generate waiting lists. Kiko has been teaching these for some time. Every time he's offered to teach other faculty members, Teresa has been teaching these for some time. She's at the back at Harvey Mudd. They sell out and generate waiting lists. We have kind of 2 nonprofit organizations. One is Alpha, but we have a strict firewall for fundraising for a number of reasons having to do with how NSF handles grant money. We have a separate foundation where we are raising a $10 million endowment. And over the past 2 years alone, we have put more than $260,000 of equipment into laboratories for use. Now, it's currently called the Jonathan Reichert Foundation because Jonathan Reichert donated his company and donated his inheritance from his father to get us started. More than $1 million of inheritance from his father. And his company is called TeachSpin. So TeachSpin is not owned by anyone anymore. It's owned by this nonprofit whose entire mission is to fund these programs. I'm the vice president. Jonathan is the president, but he gets no more vote than anybody else on this committee, which is just stuff from our people from our community, trying to make a difference. And maybe you want to participate in this sort of thing. By the way, if you come to an immersion and say you want some equipment, it's a little proposal. It's very quick. It may not be worth your time because the success ratio on those proposals is only 79%. Now, the immersions we do charge for, unlike this. But guess what? We're going to lower the cost. How low do we need to go? And one more thing. If you can't come to the immersions, we'll bring the immersions to you and your students. The food truck for the physics mind is now a real thing. Sid Harris made this cartoon for the back of the truck, and it is filled with experiments that we will bring to you. It's been in the works for some time. I'm working with, right now it has a lot of TeachSpin equipment in there. I want other equipment in there. I'm talking with Thor Labs. I want them to have things in there. And the person who's doing this is Carl Grossman, who was a professor at Swarthmore. He stepped down. This is now his life's work. By the way, the people that designed the TeachSpin equipment, David von Bach, Jonathan Reichert, people at Princeton, people all over the place, have donated 100% of their royalties from this. It all goes to these programs. That's all I have to say.
Do we have this on? Yeah. All right, well, thank you. I'm happy to be here. This talk kind of fits in the vein of what's today? Today's Sunday, Friday, more than it does today, but that's all right. We're going to go with it anyway. I was a student here 25 years ago, and I came here to do my PhD in optical sciences because it's a special place. Now, I'm here to tell you about what we're doing in Montana, and I think that's another special place. But I can never talk at a place like optical sciences without acknowledging what a special place it is and how huge the impact was of my time here on my career. And so I've spent a lot of time thinking and wondering about what made it special at optical sciences. What was different? And there are many answers to that question, but one of the answers is that it's because it's all about optics, and it's all about all of optics. And so the fact that we have pulled optics out of being viewed as a subset of physics or a subset of electrical engineering or a subset of material science or whatever you might think, and instead just said, no, it's a discipline. It's called optics, and it involves people from all kinds of backgrounds. When I was a student here, Tom, I don't know what your current makeup is, but I suspect it's not too far off. When I was a student here, we had approximately 40% of the students came from electrical engineering, 40% came from physics, and 20% came from undergraduate optics programs, mechanical engineering, material science, all kinds of different things. I suspect it's somewhat similar. And so having those different viewpoints and different backgrounds mixed together and working together is one of the things that made it very special. And that's also a key factor in what we're doing in Montana, that is done by design. And so I'm going to talk to you about what we're doing and try to tell you a little bit of a story of how we came about to do what we're doing and how that might be of interest to you. So the first thing I have to do, I actually have talked to several people that don't really know where Montana is, so I have to tell you. There's a map of the world, of the optical world, and I think we're barely on it. And so I made my map here. Montana's up here in the northwestern United States. We are in Bozeman, Montana, which is in the southwest corner, right here, just directly north of Yellowstone Park. It's kind of, we consider Yellowstone Park our backyard. It's a very outdoors-centric place. The students that, and faculty, actually, who come here to this place largely do so because they don't just value but thrive in an outdoor kind of environment. We like to ski, we like to hike, we like to fish, we like to camp, we like to do all kinds of things like that. Not everybody. I have at least one colleague who, yeah, you're smiling because you know who I'm talking about. I have one colleague who would much rather be in San Francisco or Chicago, but most of us are there because we want this kind of lifestyle. Now, why Montana? When you think of optics, many people don't yet think of Montana. I submit to you that that will change and should be changing. We have a very impressive concentration of optics happening in Montana. And so why? I mean, of all places, why Montana? Well, I would remind you that it wasn't that many years ago that the people in Rochester were looking at each other and saying, why Arizona? And so it's the same kind of thing. It's just the next thing that's happening. Here's part of why. There's something out there in the world called the laser, and it was invented, some would claim, in 1960 by Ted Maiman. And the crystal that enabled that laser to work was grown by a person named Ralph Hutchison, who's a Montana State University graduate. So it wasn't done at Montana State University. We can't lay claim to that. But it was done by one of our graduates. And one of the characteristics that we find most often in our graduates is that they all want to come home. And so Ralph was no different. After Ralph made the world's first laser possible by growing that crystal right there of ruby, he went on continuing to work at Union Carbide Corporation, where he was when he made that crystal, for a number of years. And then eventually they told him, we don't want to do laser crystals. Why don't you just take that and go and do it in your own company? And so he did. And he moved to Montana to do that. And so that's one of the big reasons that we have optics in Montana, is because of Ralph Hutchison. That was in about 1990 when that move happened. We had something going on that was called a brain drain. We were starting to do a little bit of work in the labs with lasers. We were giving degrees to students. And when you add those two things together, the outcome was inevitably a job outside of Montana. And many of our students complained about that and said, I really would like to be able to stay in state. And that was just simply not possible at the time. And so we thought about it. And the solution that was arrived at, and solutions don't happen overnight, solutions come about because of creative thinking by people that are willing to, I think, question what can be done. And the first person that I'd like to introduce you to is John. John was a professor of physics, and John liked to ski, like most people in Montana. So John went skiing one day at this ski hill called Bridger Bowl. He met a guy named Larry. Larry has a PhD in optical sciences from this place, as I do. Larry was in Bozeman waiting for a piece of equipment to be made so that he could continue his experiments at his job, which was in Minnesota. And he was getting ready to start his own company making laser diode drivers and testing equipment. And he was looking around going, I really want to be here. I like this place. And so they literally met on the ski lift. They were, oh, hi, my name's John. Hi, my name's Larry. What do you do? Lasers? Oh, really? What do you do? Lasers? And so they talked to each other, and Larry told him, well, I'm thinking of bringing my startup company. Well, there was no company yet. I'm thinking of starting up my company in Bozeman. And John said, oh, why don't you do it? Let's do it, and I'll help you, and you can help me. And so they got some activity going together. Larry's company would send a little tiny bit of money over to John's department. And unlike some people in academia, sometimes in academia, I think we have to call it what it is, folks, right? Sometimes in academia, we tend to be a little bit anti-industry, and we think, well, if my PhD graduates go on and get a job in industry instead of academia, they've failed. That's not how John thought. John thought that this would be a wonderful opportunity to train his students to think in a way that would be amenable to an option in industry if that's what they chose. And so he brought Larry into the lab. They worked together. Larry sponsored projects. And John, in addition to doing really hardcore basic laser physics, he had always, at any one time, he always had at least one student working on a project that was for this company, which is called ILX Lightwave. And many of you know ILX Lightwave because they are now a worldwide leader in the field of diode laser instrumentation. In fact, you could almost argue they are the leader in diode laser instrumentation. Okay, then a couple guys came along who you don't need to know the details about, but they were people who understood a bigger thing than John and Larry. And so they helped John put together a proposal to NSF EPSCoR, which is kind of academic welfare for states that don't have quite as much of their fair share, as they view it, of NSF funding. The university put in a little bit of, not really funding. Universities never put in funding. They put in funny money, sort of positions and time and things like that. And the state of Montana, believe it or not, actually put in some money. And together, then they created this thing called the Optical Technology Center, and I am now the director of it. John was the founding director of the Optical Technology Center, and then I took over from him 10 years later, something like that. Here are the four people who got together in a room and said, let's build optics in Montana. Let's make this happen. So there's John from physics, Rufus also from physics, Lee from chemistry, and Fred from electrical engineering. They knew that they couldn't do it out of one department alone. They knew that they needed the same mix that we have here at Optical Sciences, which is a whole world of people working together and talking together. By that time, this is the early 1990s, by that time there were four very, very young fledgling companies who were struggling to survive in town. ILX Lightwave was Larry's company. Scientific Materials Corporation makes laser crystals. That's Ralph Hutchison's company. Big Sky Laser makes solid-state lasers. And TMA and Associates doesn't exist anymore. They actually kind of do, but they've been bought and put under other names. But TMA and Associates was doing scatterometry, measurement of scattered light from surfaces to measure surface roughness. And so each of these companies had a connection to the academic people, because this company was started by an electrical engineering professor that worked with Fred. These two companies were working on laser systems that were relying on these two laser spectroscopy people to do basic science on laser crystals, and ILX Lightwave was working with John to figure out things like intensity, noise, and diode lasers. Nowadays, we have pushing 20 tenure-track faculty and a host of research faculty and staff doing optics at our university. And this is now what those four fledgling companies have turned into. This is a timeline showing the growth of companies from the Big Bang, which happened in 1980. That was the Big Bang of optics in Montana. Was a guy actually from New Mexico whose engineer was a Montana State University graduate. And when they got together and said, let's leave our federal laboratory in New Mexico and start a company, where do you want to go? The engineer said, I know, I want to go to Bozeman. And so they did. And so Orionics was doing fiber cleavers. And then you can see Big Sky Laser, TMA Technologies, that's the scatterometry company that I mentioned to you. ILX Lightwave, Scientific Materials. So by the time the early 1990s came along, we had these couple of companies that were just fledgling. And then it just sort of took off. Our center was officially recognized in 1995 by the Board of Regents. And then what our mission is really to promote academically robust optics education and research. But one of the things that we've always kept in mind, not only kept in mind, but put at the forefront of what we're doing, is we hire faculty and we do everything we can to find people who are excited about doing at least some of their work, either with or in a manner that could benefit industry. And so by populating our halls with the people that have the right attitudes and are excited about building something new and exciting, then it's really taken off. And so I don't know what the next dot will be. I can't tell you. I'm asked all the time, how do you do this? And I don't know. All I know is we're doing it. I know what we're doing, and I know what we're not doing, and we're trying very carefully to do what we think is important. But it's growing, and it's really taking off. We have most of these companies were started by our own graduates. Most of them were started by our own PhD graduates, I should add. And those students are literally coming out of a program where they have been involved with industry people the entire time. They may have been doing some hardcore laser physics experiment for their dissertation, or they may have been doing a project with industry. But they all have been exposed to an environment where entrepreneurship is natural and standard and expected. And so some of them, not nearly all of them, but some of them come out and say, I want to stay here, and there's no job for me, so I'm just going to create my own job. I'm going to start a company. And some of them leave and get experience elsewhere and then come back and start their companies. An example of that is Pete Roos. I forget who I was talking to. Somebody here knows. Yeah, I was talking to you, Jason. You know Pete. This is an example of the reversal of our brain drain. Here's Pete at about the time I came to Montana State University. Pete was a graduate student. He was taking my Fourier optics class, and I remember commenting, wow, these Montana State University students are just amazing. These guys are like they're as good as the optical sciences students were. Well, I went to find out that they weren't all quite as good as Pete. Pete was pretty good. So Pete was a student, and then now he's the CEO of one of the world's fastest growing optics companies, Bridger Photonics. And they're exciting, they're doing cool things. They make LiDARs that can measure distance orders of magnitude more accurately than anybody in the world, and they're commercializing that. And so it's really a cool story. And it's just one of many. So let me take you through a couple slides that give you a little bit of an overview of some of the things that we have going on. Again, I emphasize that one of the key things from the very beginning by design is that we wanted to cover all the way from basic science to applied engineering. And those things, I often give talks to people that are involved with the politics and the funding sources, and I try to emphasize to them especially how important basic science is, that that's tomorrow's application, or the day after tomorrow's application. And we really literally wouldn't have what is happening right now in Montana without those basic science efforts, because the fundamental laser spectroscopy of laser crystals, for example, we grow some of the best, purest crystals in the world in Bozeman, and that's what's illustrated here. And that's largely a spin-off of these really basic science labs in physics and chemistry. We also have clean rooms. We do microfabrication and nano-optics. We have a very strong program in optical remote sensing that I sort of established when I went there. This is a LiDAR system shooting through a port in the roof. We have bio-optics using MEMS kinds of systems. We have tunable lasers of a wide variety, and then we have teaching labs that are teaching students in a hands-on manner. So I'll take you through a couple slides that sort of just show pictures. These will be all pictures, no equations, very few words, just giving you an idea of some of the things that we're doing. Here's one of the company guys looking through the laser crystal. What you can't see there is that crystal's about this long. So he's looking end-on through this, almost meter-long piece of material. We have one of the latest companies, in fact, just blew my mind, because when they came out and they started making their products, I remember thinking, gosh, that's really cool, but I'm just not sure there's enough people that want those things. They're making these cryogenic stations because we had basic science going on involving spectral hole burning, where you have crystals that store and process information at speed of light, but they have to be cryogenically cooled, and that was always viewed as this really bad thing. No commercial product will ever be cryogenic. And so one of the guys went off and created a company to make these sort of coffee maker-like cryogenic machines, where you just literally hit the button and it cools you down, and it's just easy. Everything is just easy, and it works. And so, these are selling for something like $100,000, and I just thought, man, I don't know if you can sell enough of them to make a living. They can't keep up with the demand. I mean, they're getting more orders than they can possibly fill. So they're hiring like crazy, and they're making these things and selling them and shipping them all over the world. So you never quite know which one is going to hit, or you have to be smarter than me maybe to know. Lasers and optical sensors really is where we got our strong start. The laser physics background is really what sort of launched a lot of the things. And then we've looked very aggressively for applications of those in laser sensor systems. And I'll just kind of talk you through some of these pictures to give you just a flavor of some of the crazy things that we're doing. Here's the LiDAR that I was talking about. This is actually the LiDAR on the football field where we're doing range calibration. I like to say that's the most useful thing that ever happened on the football field. This picture at the lower left is an underground CO2 sensor for monitoring CO2 that's sequestered underground. This is an airborne LiDAR that's used for mapping invasive lake trout in Yellowstone Lake at Yellowstone Park nearby. This is a laser system that was designed specifically to map and track honeybees, because the honeybees could be conditioned to find a chemical that is leaking from landmines. So this is a landmine detector using honeybees. This is the next 2 or 3 generations later of the insect LiDAR, where we're now being paid by the Park Service to look at insect ecology and crazy things like that, operating out of my student's Subaru. Novel imaging methods also. I think after the lasers became a big deal, we sort of started expanding more into imaging as we hired people like me that do a lot of imaging. This is an agricultural imager that is riding in the cab of a combine to do weed mapping during wheat harvest. This is a biomedical imaging system using these small little MEMS mirrors that are made in the clean room. And these are both tip-tilt mirrors and shape-changing mirrors. So this is literally adaptive optics on a micro scale. Thermal imaging systems, we can calibrate these little, as you probably know, there's thermal imagers that are even attachments on your iPhone. And this is all made possible by low-cost uncooled detectors, and that's great, except for they really stink at putting out good images. But we can calibrate them better than anybody that we know in the world, and we can get scientific grade images out of those cameras, and so that's what this is. Balloon-borne imagers, rocket-borne imagers to study the sun. This is an agricultural imaging experiment, one of the first we did. This is an image that shows you the entire sky. The horizon is the circle on the outside. This is showing you the degree of polarization of the skylight. So we're doing atmospheric polarization imaging. That's my project, actually. So this band of red shows you where the sky is strongly polarized. That's where you can go out with your sunglasses and rotate your head back and forth and see very strong modulation between the one position and the other. The students that come to Montana State have very hands-on opportunities all the way from undergrads on up. And one of the cool things that I like to wave the flag about a little bit is that many of these projects are right hand in hand with the local companies. So these are all pictures of students doing projects with local company involvement. In the clean room, outdoors, this is a hyperspectral imaging company. Some of you students that are here from MSU may have not ever seen this picture. This is Paul Nugent when he was very young. And we were working with Rand Swanson, who runs Resonon, a hyperspectral imaging company. We're doing things. I've actually talked to you about all these things. This is the Beehive project. This is the lake fish LiDAR. The agricultural imaging, more agricultural imaging, and some ecology kinds of things. And we also do optics all the way around the world, literally from the tropics to the Arctic. And so as far as academic options, we're building all the time. Right now, as of today, what we have is the newest piece was requested by industry. Now that they've gotten their start from PhD levels work, they're starting to manufacture things, and they start needing, at that point, more and more support at each level. And so they requested a photonics technician program, so we responded by creating that at the local community college. We have a minor for bachelor students in optics and photonics. We have an actual MS in optics and photonics for the students that want that. And we have a PhD program that doesn't yet have an optics degree, but it has an optics emphasis in any of our 3 participating departments, electrical engineering, physics, and chemistry. The course topics cover pretty much the spectrum. I haven't thought of everything, but I tried to think of everything I could think of and put it down here. Some of these are things that you'll find at every main optics school. Some of them are unique: remote sensing systems, atmospheric optics. These are things that we have very strong strengths in that are a little bit unique. I'd like to tell you, especially the students, that we have an REU program for research experiences for undergraduate that is, I actually should have told you that we have another one too, but there's actually 2 REUs that have relevance to optics. One is in the physics department with solar physics, and the other one is this one that I have the title up here, which is really emphasizing kind of remote sensing, but across the spectrum from sound waves to light waves. And so if you'd like to do some experimental measurements in the lab and outdoors, there's my email. You can email me and I'll get you in contact with the people that are running that REU program. So we have a very dynamic and what I think is exciting concentration of things going on with companies, research, and students. And we invite you to come and be part of that, either as a visitor, come up and give a talk. I can help pay your way to come and visit us, or come up and collaborate with us, or come as a student and study with us. And we'd be happy to do that. And likewise, we are excited about the collaborations we have with people around the world, including here at Optical Sciences. That's continues to be a very, very important connection for me. Finally, I'd like to just blatantly advertise my book that'll be out in a couple weeks. And so this could be a good topic maybe for us to talk about next year at the thing. But many of you know that I'm an avid photographer, and I've taken thousands, if not hundreds of thousands, of photographs of optical things in the atmosphere and in the oceans. And so I have this photo-rich book coming out that will be hopefully accessible to people at all levels. I think there's enough detail in there that optics people will learn a lot, but there's enough simplicity in there that non-optics people could learn something. So with that, I'll take any questions that you have. Thank you very much for your attention.
The next speaker is Professor Enrique Galvez from Colgate University. He's going to talk about the spatially variable polarization.
Thank you very much. I want to thank the organizers for inviting me and coming here to such a beautiful place. I'm from Colgate University. I'm way up there in upstate New York. I leave tomorrow, so I'm not going to show you any white pictures to not get depressed. Colgate is a small liberal arts college. We have a bunch of undergraduates working with me, and we do have, I have a graduate student, but it's like a borrowed graduate student. He's officially from Florida Atlantic University, but he's doing his dissertation in my lab. And then we also have a postdoc, but then we have some interesting teaching research postdoc, Josh Jones. So he teaches and is also a research postdoc. And a bunch of undergraduates and collaborators and funding agencies. Okay, so I'm going to switch gears to more fundamental science, and I'm going to tell you about some particular problem that I've been working. It doesn't have to do with single photons, although I've had a lot of fun with single photons. And now the underlying themes are that is about studying complex light, and those are light beams that have singularity. So it falls under a topic that has been kind of popular called singular optics and emerging also, and involves tabletop experiments, optics experiments. Colgate, again, is a small place. And we have undergraduate researchers mostly, and except with that one exception. And so what I'm going to tell you about is a problem that involves polarization. But then since we spend most of our time teaching, then we found a way to transfer some of the research to the teaching, and then so I'm going to tell you a little bit about this, how to rethink how we teach polarization, then tell you about the specific problem called polarization disclinations, and then I hope I have time to tell you about this one, which is light polarization describing Mobius strips in three-dimensional spaces, and that's going to be the talk. States of polarization, we all know about linear polarization. These are the horizontal and vertical vectors, amplitudes. And for linear polarization, the horizontal and vertical components are in phase or out phase. You know all of that. And then here's some notation. These are the unit vectors. And then circular polarization, again, the amplitudes of the two components are the same, but they're out of phase by 90 degrees. So then I represent that by I there, and then there's a picture. I am going to define these states of circular polarization as superpositions of x and y vectors out of phase by 90 degrees. They'll become useful later. And finally, elliptical polarization is a more complicated case where the amplitudes may not be the same, and then there's a phase difference between the two components, and then what you get is an ellipse. And that's the ellipse. Okay? And well, how do we characterize the ellipse? It has an ellipticity, which is the ratio of the semi-minor to semi-major axis of the ellipse. And it's, in general, tilted by some angle theta. And then the ellipticity can be characterized by some angle chi. So we look back at the general state of polarization, and instead of putting Ex and Ey, I just put them in terms of some cosine of alpha and sine of alpha, just to say that the X and Y components have different amplitudes. And there's a phase. Then we look at that and we say, how do we relate the amplitude and phases of the elliptically polarized expression to the parameters of the ellipse? And you saw that. Not trivially. And so then what do we do normally? Well, that's too complicated. Let's just skip it. So all you need to know is linear and circular, and elliptical is somewhere there. Who cares? But turns out that linear and circular are the exceptions, right? Whenever you look at polarization, it's elliptical. And so it's important to give it a better coverage. Okay? So what do? Well, we recur to this very extremely smart gentleman, Henri Poincaré. Just to give you a flavor of him, he founded topology. He worked on differential equations. He proposed length contraction. He was one of the pioneers of relativity. And in fact, he published all his stuff about relativity by the time Einstein came up with this paper on relativity. And he was so grumpy about it, he never cited Einstein because he thought he was the creator of relativity. And then he was also very famous for the Poincaré conjecture of topology that lasted almost 100 years. And it was solved in 2002. And I won't get into that. And he proposed gravitational waves, okay, way back there in the turn of the 20th century. So, well, anyway, so he defined this sphere in 1892 called the Poincaré sphere to map all the states of polarization in this sphere. So the North Pole is circular, right circular. The South Pole is left circular. The equator has linear states of polarization. So any arbitrary point on the surface of the sphere is elliptical. But what is interesting is that points that have the same latitude have the same orientation. So go like this. These guys have all the same orientation. And then points that have the same longitude have the same orientation. Points that have the same latitude around here have the same ellipticity. So the ellipse shape remains the same, but as you go around, they have different orientation. So we can represent a state of polarization in terms of right and left circular states. And when we do that, the ratio of amplitudes tells you the ellipticity, and the ratio and the phase difference tells you the orientation. Okay, so the only thing we need to do just to get a picture from equation to ellipse is to go back to the circular representation. Anyway, so we did that. And another thing is, if you want to go in the opposite direction, you measure a beam of light. How do we know what's the state of polarization? There's a very clever way with what are called Stokes parameters. And basically, you end up measuring the coordinates of the point on the sphere. And you use measurement of the light with different filters, right, left, polarization, horizontal, vertical, diagonal, anti-diagonal. Once you have those coordinates, you can eventually find chi, this angle, the polar angle that gives you the ellipticity, and the orientation of the ellipse, which is the azimuth on the sphere. Anyway, so you can, so then we want to measure polarization. How do we measure polarization? One way to do it, simply, is with these four elements. And suppose you have an ellipse. You have a half-wave plate. You rotate the ellipse to be horizontal. Then when the axes are horizontal vertical, then the phase difference between the two components is 90 degrees. So we pass them through a quarter-wave plate that adds a phase of 90 degrees. So elliptical becomes linear. So after linear, you put a half-wave plate that makes it horizontal, and here you put a horizontal polarizer. So this is a filter that filters out any states of elliptical polarization. But what is interesting is that this component adjusts the orientation, and this component adjusts the ellipticity. So we came up with this, let's say, curriculum, how to teach polarization, and then we created a beam that where the polarization varies from point to point. And then the students would use this way of detecting the light as a way to find out what is the polarization of each point on the beam of light. And then if you set up the last polarizer so that you block the particular state that you want, your beam will have a hole in it. And then as you change orientation and ellipticity, this hole moves around. And then it has a small apparatus. And recently we published this in the American Journal of Physics in the November issue. But I haven't told you how I make this state, this beam where the polarization varies from point to point. So I'm going to do that now. So to get started on generating that beam, we need to talk about these mode, Laguerre-Gauss mode. So it's a beam where the amplitude has this form. This is a Gaussian, and then it is r to some power L. So when L is equal to 0, then this goes away, and then we get a Gaussian. That's your regular laser beam, like this pointer. And the phase is flat, the same for the entire beam, and the wavefront are planes. And but now, when L is not 0, you have this phase that varies with the angular coordinate. So if I now put, say, L equals 1, and look at the phase of the beam, it varies with angle. Here I'm encoding it in color. So then the wavefront, the points that have the same phase, have this corkscrew shape. And now L equals 2 would be another donut like this one, and but now the phase changes by 4 pi as you go around. And of course the center is dark because it has all the faces. And now the wavefront is a double spiral. And you can keep going. L equals 3, you get 6 pi, and your wavefront is fusilli pasta. And but then what is interesting about these beams is that they carry orbital angular momentum. There's a certain type of angular momentum, not circular polarization, that has to do with this tilted wavefront. And you can transfer that angular momentum to light beams. And how do we generate these beams? We use a very peculiar diffraction pattern that has a fork in it. And then the diffraction orders have these donuts. And then it's extremely cool. The different orders have all these beams of different phases. Okay, so that's the first requirement. So now what we're going to do is we're going to combine one of these beams where the phase varies with the angle, right-handed polarization, with another beam that the phase is flat with left circular polarization. But if you recall, the orientation of the polarization varies with the phase difference. But this one changes the phase like this, and this one has a flat phase. So the orientation is going to change around the beam. Although if we don't put any polarizers, the beam is going to look pretty dull. So if we express this equation in terms of right and left circular polarization in this form, we find that the ratio of amplitudes depends on R, and the phase difference depends on the angle. So this is a beam of light where the polarization changes from point to point, and the ellipticity varies with R, the orientation varies with phi. So there's the beam again. One more thing, I won't get into photons, but this is a non-separable superposition. And then some people call it classical entanglement. Other people see red when they hear classical entanglement. But I won't go further. But some people are working on that problem. But I won't get into it. And then this is the prediction. And then there's your beam. The center is almost circular. And then it becomes linear. And then circular of the opposite ellipticity further out. And then the orientation varies around. This is a so-called radial beam. And you can also do plus L and minus L, and then you get another form of the radial beam. And then these things have been studied for a while. We studied them in 2012. But there's more, okay? Because these patterns are pretty intriguing. So what I'm going to get into is digging deeper into these patterns that the polarization traces. And they're called disclinations, which are dislocations in the rotational order. And then you can find them in topology. Say that if you have an ellipsoid, the curvature of any particular point can be split into two parts. One, the maximum radius of curvature, and the minimum radius of curvature. And those 2 points, those 2 axes are orthogonal. So if you trace out the axis of the greatest and lowest radii of curvature, you get these shapes. And this point here is some point on the sphere that is spherical, so there's no preferential greater. In all directions, the radius of curvature is the same. And even today, in mathematics, there's this Cassiodari conjecture that is an open problem since the 1920s. That there's actually some mathematicians that have found a solution to this, which is currently under review. But since 2015, mathematicians take a long time to review their papers. But it's a very important problem in topology. But here are other disinclinations. This is you can see that the lines reach a dead end here, and then some funny shape happens here, and so on. Well, in liquid crystals, you also have disclinations in the directions of the liquid crystal molecules. At some point, you reach a point where they just don't know where to go, and then you get a singularity or a singular point. And finally, cosmic background radiation has these polarization maps that are supposed to give us information about what happened in the early Big Bang. And then these are data from BICEP 2, which turn out not to tell us much about the Big Bang, because apparently a lot of these fluctuations are caused by dust in the galaxy. But then there's another effort to do it right, and that's called BICEP 3. But the idea is that the polarization disclinations in the cosmic background radiation are supposed to tell us about the inflation and the Big Bang. So we want to study these type of patterns with light. And so we do it with light's polarization. So if you look at disclinations, these are the simplest ones. And you think about this, you think of an arrow tangent to these lines. As you go around, this arrow flips direction by 180 degrees. So then the center is a singularity in direction. And here you have another case, but now the arrow changes by flips, but in the other direction. And this is called a lemon, that's called a star. The index means half a turn in one direction, minus one half a turn in the other direction. And you can correlate the index to how we make the beams. We put, if you recall, we have a vortex that has this L of one kind with right-handed polarization, and the other vortex with another L and left-handed polarization. These are the two values. So if I do 1, 0, I get this lemon. And if I do minus 1, 0, I get the star. So now these are modeled patterns. And also there are these peculiar lines called radial lines that are part of the topology of these patterns. Now something about the color, okay, is false color. And the color is the orientation of the polarization relative to the radial direction. So wherever you see these radial lines, you'll see yellow. So that's yellow, yellow, and then, so that's a way to compare this with that, okay? Because all these little ellipses can get you a little dizzy. Okay, so then this is an apparatus. How we do this, we use spatial light modulators, which are the coolest devices. They are programmable diffraction gratings. In fact, what's in those projectors is a spatial light modulator. And that's how it projects all these cool things. And but now we get to program them, and we program them to have a phase that has the phase increases by L as you go around, L times 2 pi, and then here's L1 and L2, and eventually we have imaged that into a camera, and then that's the apparatus. If you can see, it's pretty small setup, tabletop. And okay, so let me keep going. And so now we've been doing this effort to create these patterns in what we call the near field, because we get to less distortion than projecting the beam in the far field. Okay, some optics trick. So then here we have again now a measurement of the lemon. This is the predicted pattern, the modeled pattern, and then that's the measurement. And then you have the star. And you can see we are doing nice. We're having a lot of fun. You can do these patterns with all the combinations of L's, the vortices on each beam. And then we can get into all these things, the radial lines. Here there's one radial line. Here you have 3 radial lines. Again, the color yellow, it tells you the radial directions. And this has been worked out by various people, but we were curious about, well, what if we just keep going to higher disclinations? So we get into higher order disclinations. So you get a hyperlemon that some people think that it looks like a spider, so they call it a spider. And then you have a hyperlemon that some people call it a flower. Okay, and then this other one, when the index is negative, you get a spider web. So So you can see we're having a lot of fun with all those disclinations. And interestingly, how do we determine the index of these patterns is done with a formula that derived by Bendixson in 1901. And Bendixson was following the footsteps of Poincaré. So it's kind of nice that we get to cite a paper from 1881 and 1901. So, but then there's more. And then we're getting close. And then we published this recently, and then we got some cover, which was nice. Now, for a while, there were these are researchers that predicted a new type of pattern that is odd, is neither a lemon nor a star proper, because it has these other sectors. And it called it a monstar. And of course, when I told that to my daughter, she said, "Oh, monsters! I know monsters." So then we did that, and then we found really cool shapes. And okay, so I'm going to bore you with shapes, but then we found these monsters, and we are in the process of publishing all of that. And then let me say that also related to this, we have. I have a college student here. I don't know if he's right there, Ben Savaric, and he's also created monsters, but now not exactly with SLMs, but with these new devices called Q plates, which are really cool, invented by some colleagues in Italy, and then his work is just beautiful. And then his data is gonna go straight to a paper, and we're gonna start working on it pretty soon. And anyway, so that tells you the idea of just us going to the deep end, in terms of creating different line shapes with polarization of light. And that has been our interest, to figure out this problem. But now there's one last problem before I end. That is, all these beams were collinear. Okay, what if the beams are not collinear? The beams are not collinear. Okay, we have some equations. Okay, you don't have to pay attention too much to the equations. Each has a reference frame. The important thing is that when you look at the expressions of the electric field in the plane where we're going to put a camera, there's a z component. Each of them, because of course they're coming at an angle, so then the electric field that is transverse to the wave has a z component in this plane that is not perpendicular to each of the beams. And that's interesting. Okay, so we keep digging. Okay, and so then if we have, this is a regular pattern when the two beams are collinear, theta equals 0. But if we start changing the angle, all of a sudden the pattern starts to get squeezed in one direction, and we start getting very peculiar patterns of polarization. So then you could think of this as a polarization diffraction pattern, where what is varying here is not the intensity, but the state of polarization. Sounds cool. Okay. Is there more to it? And the answer is yes. And if you look at the interference pattern that is created, and then you play some tricks, do some measurements, and find out what is the orientation of the semi-major axis of the polarization ellipse. Because there's this location there in the middle, what happens is that the polarization ellipse actually twists in 3 dimensions. And it may or may not reconnect when you go the full circle. When it doesn't reconnect, you have a Mobius strip. When it does reconnect, it's called a twisted ribbon. And so that we've been working on this problem. So at different radii, you have different Mobius strips. And so can we measure this? And the answer is yes, we can measure it. And this is a simulation of one of these cases. And this is one of our measurements. We figured this problem only recently, so this is just preliminary. But it's pretty cool that to find out that the light is kind of has this very rich behavior in 3 dimensions when we intersect beams that have these peculiar properties like phase vortices. Okay, so that's really kind of a flavor of what we've been up to at Colgate, again, playing with classical beams of light. So I'll end with a thought, okay? And this is a quote by Albert Szent-Györgyi. He's a Nobel laureate in medicine from the 20s, which is, research is to see what everybody has seen and to think what nobody has thought, which is really what we do in optics. We see all these beautiful things, but most of the time we don't have a clue, right? And then the fun part is really to figure it all out, right? And then, of course, I'm biased towards singularities, so, of course, singularities are telling us something. We just have to figure out what that is. And so with that, I thank you for your attention.